Chapter 2, Section 4, the chain rule. The chain rule is used when we are trying to find the derivatives of composite functions. As I've given a couple of examples up here, the sine of x squared plus 3, the square root of x squared plus 1. These are composite functions because you have an inner and an outer function. You have to kind of think of this as what's my inner function, what's my outer function, what's my inner function, what's my outer function. I always think of it as if I plug in a number for x and attempt to evaluate the expression, the first thing I would do is the polynomial, then I would take the sine of it. So the first thing I would do is the inner function, the last thing I would do is my outer function. If I was to plug in a number here for x, like I plug in 1, first I do the polynomial and figure out that this is 2, and then I take the square root of it. So that's the second thing is my outer function. Keep track of that because what you're going to try to do is you're going to try to take the derivative to begin with of the outer function with respect to the inner function times the derivative of the inner function. So if we think of dy dx where we have a third variable and that variable being the inner function, call it u, we are trying to find dy du times as fast as u changes as du dx. So the inner function is changing, and then you've got to take the outer function changing that with respect to the way the inner function is changing. So it looks like dy du over times du dx. It's almost if it looks like those cancel. It doesn't work that way, but that's kind of how it looks. So what we're looking for is the chain rule, and I'm going to read this. If u changes, or if y changes dy du times as fast as u, and u changes du dx times as fast as x, then y changes dy du times du dx times as fast as x. Kind of like if you have gears. You might have a small gear. This is going to be a terrible drawing. Stop me now. And then you have a larger gear. And I didn't get it close enough so that it's changing. This is moving, this is making this move faster because this is larger. Just like changing the gears on your bicycle, if you have a bicycle that has the different speeds on it. Well, that was a terrible analogy. I should probably start this whole video all over again and come up with a better one, but I'm not. The theorem is called the chain rule because it has links that join together to make the derivative. If y equals f of u, be careful, is a differentiable function of u, and u is equal to g of x is a differentiable function of x, then y equals f of g of x is a differentiable function of x. And dy dx is equal to dy du, that's the derivative of the outer function with respect to the inner function, times du dx, which is the derivative of the inner function with respect to x, or equivalently, the derivative with respect to x of f of g of x is f prime of g of x, the derivative of the outer function with respect to the inner, times the derivative of the inner function with respect to x. Okay, again, it's important to think of this as having an inner part and an outer part so that you can know how to set up your derivative. For example, all I want to do here real quick to start this problem off is figure out, I have a composite function, what's my inner part? Well, if I plugged in a number for x, the first thing I would do is be 5 times x. Therefore, this is my inner function and this is my outer function. Now, the derivative of cosine is negative sine. So, if I want to find the derivative here of the cosine of 5x, it's negative sine of 5x times, that's this first part right here, the derivative of the outer function with respect to the inner function, times the derivative of the inner function. The derivative of 5x with respect to x is 5. Now, it might help you if you say, well, let u be 5 times x. So this is y equals the cosine of u. Well, you know that this is y prime is equal to negative sine of u, but since u is a function of x times, the derivative of u with respect to x. So the derivative of u with respect to x is the 5. And then plug back in. And I get right back to here. And I'm not going to leave my answer that way. I'm going to write y prime equals negative 5 times the sine of 5x. Now in part B, I'm going to think of this as 2x squared minus 5 to the 1/2 power. See, my inside function is the polynomial, kind of like it was back here when I was looking at this first example. I almost hate to show this drawing again. Okay, but now my outside function is the square root or raising it to the 1/2 power. My inside function, my outside function. So y prime is first the power rule with respect to this. It's not x to the 1/2. It's this differentiable function of x to the 1/2. So this is 1/2 of that differentiable function of x to the negative 1/2. Hopefully you can see that. That's a negative 1 there. Times, that's the first part. That's this part. The derivative of the inside function with respect to x, which is 4x. The derivative of 2x squared minus 5 is 4x. So now I'm going to write this. I'll multiply the half times the 4x. I get 2x times the quantity 2x squared minus 5 to the 1/2, negative 1/2, excuse me, or 2x all over the square root of 2x squared minus 5. I went ahead and wrote that negative 1/2 as the positive 1/2 in the denominator, and then wrote it with the radical symbol. I don't like a negative exponent in my final answer. It doesn't seem simplified. This problem is a little bit like the last one, except that I don't have a square root. It is being raised to a power, this time to the power of 4. So this is my inside function, and this is my outside function. Okay? So my outside function, if I take the derivative of that with respect to my inside function, this would be, bring the exponent out in front. This is the power rule. 4 times this quantity here, this function, this u, to the 4 minus 1 to the 3rd power, times the derivative of the inside function, which is 3x squared plus 5. So that gives me, I would probably write this as 4 times the quantity 3x squared plus 5 times the quantity x to the 3rd plus 5x to the 3rd power, like that. I don't think I'd multiply all this out. I certainly don't want to cube this. I mean, I guess I could distribute here by the 4, but this is good enough. One more coming up, and you must practice this. Most of the functions that we deal with are composite functions, so you have to get used to the chain rule. You got the sum and difference, you got the product rule, the quotient rule, and now the chain rule. All right, so y equals the sine of x squared plus x. If I plugged in a number for x, first I do the polynomial, and then I would take the sine of it. This is my inner, this is my outer. So y prime would be the derivative of the outer function with respect to the inner, so it would be the cosine of the quantity x squared plus x times the derivative of the inner function, which would be 2x plus 1. By now you should be able to see that the derivative of this is equal to this pretty readily. I don't think I'd leave my answer like this as well, because it almost looks like I need to multiply these two expressions in parentheses, and that's not the case because this is the cosine of this expression. I would probably write the quantity 2x plus 1 times the cosine of the quantity x squared plus x. That looks a little less confusing, at least it does to me. All right. Now you'll notice that on examples B and C, I had kind of a weird looking power rule where the first thing I did was I took the derivative with respect to the exponent. Well, we can kind of generalize that, and you'll see why I use that expression, and come up with the theorem which we call the general power rule. The general power rule involves the chain rule. It's just one specific type of example. It just happens to be one of the most common of the types of an example. And it says let y equal u of x raised to the nth power, where u is a differentiable function of x and n is a rational number. Then the derivative of y with respect to x, notice what they do. They just pop that n out in front, the inside function, to the n minus 1 times the derivative of the inside function. All right. Now I'll show you here with a couple of examples, three examples. This is my inside function. This is my exponent. This is the general power rule. All right. So based on this, y prime, bring the 10 out in front, times the quantity x squared plus 3 to the 10 minus 1 or 9th power. That's the first link in the chain. This is the second link. I have to take the derivative of the inside function. That would be 2x. I don't think I'd leave my final answer this way. 2x times 10 is 20x times the quantity x squared plus 3 to the 9th power. Certainly don't want to expand that. The next guy up is very similar, except I'm going to be working with a negative exponent because I'm going to write this as 5 times the quantity x squared plus 1 to the negative 3 power. Now I'm going to use the general chain rule. G prime of x is equal to, bring the negative 3 out in front, that would give me negative 15 times x squared plus 1, subtract 1 to the negative 4 times the derivative of the inside function, the x squared plus 1, and that would be 2x. So this is going to give me, I'll put it below here, negative 15 times 2x is negative 30x, all over, and I don't like those negative exponents in my final answer, to the 4th power in the denominator. This is g prime of x. This third example here is going to use the general power rule, but it's also going to use the product rule, because this is the product of x to the third and the quantity 1 plus x squared to the 1/2 power, so that I can use the general power rule. H prime of x is equal to the first one, x to the third, times the derivative of the second. Here's the general power rule. So this would be times 1/2 times the quantity 1 plus x squared to the negative 1/2 times the derivative of 1 plus x squared, which is 2x. All right, that's the first part. First one times the derivative of the second, plus the second one, which is the square root of 1 plus x squared, times the derivative of the first, which is 3x to the second. Now, I can do some work on this. I can knock out a 2 here and a 2 here. I have an x to the third, I have an x here. I can write this as x to the fourth, all over, because it's a negative exponent, the square root of 1 plus x squared, and then this would be plus 3x squared times the square root of 1 plus x squared. Now, I don't hate this as a final answer, but it probably isn't going to match the answer in the back of the book. Whoop, I'm all cattywampus there. All right, what's going to probably happen is they're going to get a common denominator, which would be the square root of 1 plus x squared. So if you multiply top and bottom by the square root of 1 plus x squared, you're going to get rid of the radical in the numerator. So it's going to give me x to the fourth plus 3x to the second. It would be this times this, so it would be the quantity 1 plus x squared, oops, forgot the 1, all over in the bottom, the square root of 1 plus x squared. Now if I distribute up here, I'm going to get a 3x squared plus 3x to the fourth. I already have an x to the fourth, so that's going to give me 4x to the fourth plus 3x squared, got a little fancy, combined a couple steps, all over the square root of 1 plus x squared. See, that to me is a better looking answer than this was. Okay? Especially if we're doing extra steps here, as we will be in the next chapter. So try to get used to writing expressions like this as a single expression. Next example, it says find all points for which f prime of x is equal to 0 or f prime of x does not exist. And we have another product rule, but we have a product rule that involves the general power rule because it's to the 1/3 power. So f prime of x is equal to the first one times the derivative of the second, that would be 1/3 times the quantity x minus 1 to the negative 2/3, subtracted 1, times the derivative of x minus 1, which is just 1, chain rule, plus, or excuse me, minus the second one, which is x minus 1 to the 1/3 times the derivative of the first one, which is 1. So up top, let's see, I'm going to have x all over 3 times the quantity x minus 1 to the 2/3. And then here I'm just going to have minus, this is going to be the cube root of x minus 1. Well, let's get that common denominator again. That means I have to multiply top and bottom by 3 times the square root, excuse me, 3, let's just write this a little bit nicer, 3 times x squared minus, x squared, good lord, x minus 1 to the 2/3, top and bottom. So this is going to give me, good thing I have a little extra space here, this is going to give me x over 3 times the quantity x minus 1 to the 2/3 minus up here, that's going to give me, this is to the 1/3 to the 2/3 to the first, so this is just going to give me 3 times x minus 1 all over 3 times x minus 1 to the 2/3. So this is going to be common denominator I have x minus 3x plus 3 is going to give me negative 2x plus 3 up top. Now nothing cancels top and bottom. Sometimes actually something will. So I feel pretty comfortable with this answer. I am going to go ahead and write it kind of like almost a summarization here. That's negative 2x plus 3 all over 3 times the quantity x minus 1 to the 2/3 power. All right, now I'm not done, but I'm really close to being done because I have to find that when f prime of x is equal to 0 or when it doesn't exist. As you can see, it doesn't exist when x is 1, right? Because you get 0 in the denominator. And it's equal to 0, f prime of x is equal to 0 when you have a fraction, when the numerator is equal to 0. When negative 2x plus 3 equals 0, or when x equals 3/2. And of course it's undefined when I have 3 times x minus 1 to the 2/3 is equal to 0, which means this is going to be at x equals 1. So it says here, find all points for which f prime of x is 0 or f prime of x doesn't exist. It does say points, so I'm going to plug into here. Now notice, even when this one where it makes it undefined, it's defined for the original problem. So my points are, let's see, if I use the 3/2, something tells me this is going to get messy with arithmetic. This is going to be 3/2 times the cube root. 3/2 minus half would be a half. So this would be 3/2 times 1 over the cube root of 2, multiplied top and bottom by the cube root of 4. I would get 3 cube roots of 4 all over 4. Yikes. What a mess. What have I gotten myself into? And when x is 1, this should be easier. Yep, it's definitely easier because when x is 1, f of x is 0. And those would be the 2 points in question. All right. Now let's combine like the chain rule and the quotient rule and the product rule as well as let's get to some of these trig functions using the chain rule. All right, so let's start off with differentiate. This looks like a quotient rule. I would probably think of this, where's my other pencil here? There it is. I would probably think of this as 2x all over the quantity x squared plus 4 to the 1/2 power. So I can kind of use that when I'm doing my low-d high minus high-d low stuff. I hope I left myself enough space. F prime of x is equal to the denominator, x squared plus 4 to the 1/2 times the derivative of the numerator minus the numerator times the derivative of the denominator. This is the generalized chain rule. So that's 1/2 times the quantity x squared minus 4, x squared plus 4, excuse me, to the negative 1/2 times the derivative of the inside function, which is 2x. Yikes. All over my common denominator, which all over my denominator squared, which is x squared plus 4. All right, what a mess this is becoming. So this is 2 the square root of x squared plus 4. These twos cancel. This one doesn't, so I have an x and a 2x, so minus 2x squared all over the square root of x squared plus 4 all over, think of it as x squared plus 4 to the first power if you want to, because I'm going to get rid of that. I am going to multiply top and bottom by this denominator. X squared, let's see, hopefully I'm keeping this even enough, x squared plus 4, x squared plus 4. So f prime of x, up top, I distribute 2 times the square root of x squared plus 4 times the square root of x squared plus 4 is just 2 times x squared plus 4. Minus, here when I multiply, these cancel and I just get minus 2x to the second all over my denominator. Now this is to the first, this is x squared plus 4 to the half. So this is x squared plus 4 quantity to the 3/2. Now if I distribute, I get a 2x squared and I have a minus 2x squared, so that's cancels. And so I just get 8 all over the quantity x squared plus 4 to the 3/2. Well, I bet you when you were at this problem right at this point right here in the problem, I bet you didn't think it was going to simplify all the way down to this. And it just takes practice to get to the point that you can do this without it taking 3 times longer than it takes me. It just takes a little bit of practice to get good at this. All right, now we have another generalized power rule here, but in this case, my inside function is a quotient rule. So I have to be careful here. Now I could square the numerator and denominator and do it as a big old quotient rule, but I'm going to try it with this, with the power rule. So that's 2 times the quantity x squared plus 2 over 2x minus 5 to the first power times the derivative of the inside function, which is low d high minus high d low over the square of what's below. So what do we have up here? We have 2 times x squared plus 2, quantity up here, times, oh, that's all over 2x minus 5, times, up here, I get 4x squared minus 10x minus 2x squared minus 4. Yikes. All over the quantity 2x minus 5 quantity squared. Well, I can do something with those denominators. That gives me 2x minus 5 to the third power. Can you see that okay, I hope? To the third power up top, I have 2 times x squared plus 2 times 2x squared minus 10x minus 4. Well, nothing cancels, but I should try to factor this to make sure nothing cancels. I could pop a 2 out, because 2 goes in all 3 terms. If I did that, I would get y prime and bring the 2 out in front. That would be 4 times x squared, the quantity x squared plus 2, times x squared minus 5x minus 2. Hopefully you can read this. All over the quantity 2x minus 5 to the third power. Now, before you start doing a lot of woe is me, as much work as that took, think about trying to do this using the definition. I don't. We would be at it for days. In this case, because we can use the chain rule, we can use the quotient rule, we're able to cut through a problem like this much more efficiently. Okay, just understand that not all problems in calculus can be done in 5 seconds. Okay, or if you want to try to get them correct. All right, now the trig functions in the chain rule. If u is a differentiable function of x, then the derivative of the sine of u is cosine of u, but times the derivative of the inside function, the inside function is u each time, times du dx. The derivative of cosine of u is negative sine u times du dx. Notice that it's exactly the same, except that it has the chain rule effect of the du dx. So if I ask you to differentiate the cosine of 2x, y prime would be negative sine of 2x times the derivative of 2x, which is 2, or negative 2 sine 2x. The derivative of the cotangent of x squared, here my inside function is x squared, y prime would be negative cosecant squared of x squared times the derivative of x squared, which is 2x, or negative 2x times the cosecant squared of x squared. All right? This next guy here looks nasty, but the sine of 2, remember, is a constant. They try to fake you out here. This is not 2x cubed. This is the sine of 2 times x cubed. So this is just a constant. So y prime is just the power rule. Bring the 3 in front. Times x, subtract 1 from the exponent. 3x squared. Almost done. Save the best one for last here coming up. All right, now this, in this case, it's still a chain rule, but my inside function is not what I'm taking the sine of. It's the sine of x itself. So my outside function is the exponent. So this is a generalized power rule. Bring the 3 out in front, times the sine squared of x, times the derivative of the inside function, which is the sine of x. So that would be the cosine of x. Now, here's a great example of a problem where you look at it and you say, no problem. That's going to be the answer in the back of the book. Then you look in the back of the book, and they've done something a little weird. They've written 3 as 3/2 times 2 times the sine of x times the sine of x times the cosine of x. And then they look at this and they look at this and they say that's the double angle sine. So they write this as 3/2 times the sine of x times the sine of 2x. You never know with some of these trig substitutions. Again, this is a perfectly good answer. But if you get an answer that's kind of got a 2x in there somewhere, you got a feeling that they must have made a substitution. This guy is a lot like the last one because I can think of this as the tangent of x to the half. So y prime, first the outer, that's the exponent, power rule, generalized power rule, to the -1/2 times the derivative of the tangent of x, which is secant squared of x. So I end up with secant squared x all over 2 times the square root of the tangent of x. And as I said, I saved the best for last here because this is a composite function, but it has 3 parts. There's an inner function, that's the 2x. There's a middle function, that's the cotangent. And then there's an outer function, that's the exponent. If I plugged in a number from x, first I'd multiply by 2, then I'd take the cotangent of it, then I'd raise it to the 4th power. Inner, middle, outer. So first the derivative with respect to the outer function. So that's all of this to the 4th power. So I pop this generalized power rule, pop the 4 out in front, subtract 1 from the exponent. Okay. Now I'm taking the derivative of the middle function, which is a cotangent of something, of 2x. So this would be negative cosecant squared of that 2x times the derivative of the innermost function. The derivative of 2x is 2. So I have a 4, a -1, and a 2, so that's -8 cotangent cubed 2x of 2x, cosecant squared of 2x. Oops, 2x. And that's how I'd leave my final answer. And as you don't even probably need to hear me say it, to do the chain rule, you just have to do enough of the examples and types of problems so that you feel comfortable with it. So I'm going to go ahead and say it anyway. You must practice, practice, practice.